Alright, what's up guys? In this video, I'm going to pick up some vector calculus and we're going to be talking about line integrals on closed curves. So it just has to evaluate this line integral for the given vector field, which is given by f down here, and a closed oriented curve C by parameterizing C. And they basically tell us here that C is a circle of radius 8 centered at the origin. And so they want us to evaluate the line integral. So the first thing we need to do is to parameterize the circle. So let's begin by doing that first. Okay, because that's what C is. It's a circle of radius 8 centered at the origin. So to parameterize the circle, remember, that's just going to be x is equal to r cosine theta, y is equal to r sine theta, and we know that theta will be in between 0 and 2 pi, or actually t would be in between 0 and 2 pi, because we're going to evaluate in terms of t. So actually t is between 0 and 2 pi. And we already know what r is because r represents the radius. So all we have to do is pretty much just plug it in, and then we'll need to compute the line integral f dot dr, which is pretty straightforward. We've done that before. So here r is going to simply be 8. So that means that we'll have x is equal to 8 cosine theta, and we'll have y is equal to 8 sine theta. Okay, and again, it's actually, we're going to evaluate it in terms of t, so it's actually going to be, t is going to be between 0 and 2 pi, as opposed to theta. All right, so remember how you do this. So the line integral for the line integral, it's just going to be, in this particular case, it's a closed curve, so that's why it's got the circle on the integral there. And it's just going to be f dot dr, and that's just going to be equal to the integral from a to b. It's going to be f of r of t dot r prime of t dt. So that's the formula, and it's just the dot product basically. Now remember that f is conservative f is basically conservative if, when we evaluate this line integral f dot dr, if we end up getting 0, then f is in fact conservative. So it's just something important to keep in mind. So let's keep going with it. So the first thing we'll need to plug in. So f in this case, again, we're just using our parametric equations after we parameterize this circle. Again, up here I want to just specify, when we're parameterizing the circle, it's going to be r cosine theta, r sine theta, well, x is equal to r cosine theta, y is equal to r sine theta, where technically theta would be in between 0 and 2 pi, but again, we're using the variable t, so that's why I wrote t instead. So follow me on that. So all I'm going to do is I'm going to take the thetas and replace it with t. So I just want to clear that up before there was any confusion. So this would be 8 sine of t, comma, 8 cosine of t. That's what we'll have for f if we plug everything in. And then we'll need r of t. And r of t here, it's going to be 8 cosine of t, 8 sine of t. Tried to fit it in there. Hopefully I was able to get it in. Now we need the first derivative. So we need r prime of t. So r prime of t in this case, we'll take the derivative. It's going to give me negative 8 sine of t, comma, 8 cosine of t. Okay, just wanted to fix that right quick. Okay, so it's a pretty straightforward process at this point. So we'll go ahead, get another sheet here. Okay, so all we have to do is take the dot product now. So we got f dot dr. Okay. We know the limits of integration. Limits of integration are going to be from 0 to 2 pi. And we'll take the dot product. So it'll be 8 sine of t, comma, 8 cosine of t. And we'll take the dot product of that with r prime of t, which was negative 8 sine of t and 8 cosine of t. dt. Had to fit it over there. Ran out of room. Okay, let's keep going with this. So this would be from 0 to 2 pi. And it looks like we'll get negative 64 sine squared of t plus 64 cosine squared of t dt. And we clean it up a little bit. So what I'm going to do is I'm going to factor out a 64 because we had a common factor of 64 on the inside. And so essentially what that will leave me with on the inside is minus sine squared of t plus cosine squared of t, which is cosine of 2t. So this will just become cosine of 2t. And again, it's going to be from 0 to 2 pi and integrated with respect to t. And hopefully you know how to integrate that, but if you don't, all we do is a u substitution, and you pick u to be 2t, and then du is 2dt. Then we get 1 over 2 du is equal to dt. So we got our 64, we got our 1/2, and then we just have the antiderivative of cosine of u du, which we know is positive sine of u. We can take care of simplifying the constants on the outside. So I'll come down here. So if we simplify the constants on the outside, we'll have 64 times 1/2, which is 64 divided by 2, which is 32. So we'll have 32 out here. Antiderivative, that's positive sine of u. Now we'll need to change the limits. So remember, u was 2t, so we change the limits. So we'll sub in a 0, which obviously gives me 0. Then we'll sub in a 2 pi, and that gives me 4 pi. So now this is from 0 to 4 pi. Now remember, sine of 4 pi is 0. Sine of 0 is also 0. So we'll just simply get 0. Then we'll have to multiply the constant by 0, which is also 0. So our final answer here, and since we end up evaluating this line integral, we end up getting 0. So we know that f is conservative. We could say that f is conservative because we got 0. And that's pretty much how it's done. Okay, so the only hard part of something like this, I think maybe for some students, is to go back and review or go back and remember how to parameterize certain types of figures. So that includes circles, ellipses, spheres, things like that. You want to go back and review that. That's typically covered in Calc 2. It may vary. I didn't start learning how to parameterize things until very early Calc 3, but it could well, no, it might have been Calc 2. I can't remember, but somewhere around there, they'll start teaching you how to parameterize certain types of curves, certain types of figures and what have you. They'll teach you that stuff, and you need to kind of memorize that so that you can know when you're given a certain figure what the respective parameterization for the following figure will be. Now, you'll get used to working with things like circles and ellipses and stuff like that. You'll be doing that stuff all the time, so it's not as hard as it seems to kind of remember the parameterization. And then after that, I mean, it's just a simple substitution process. You take your dot product, make sure you're taking your derivative correctly, go through and deal with the integral, and that's pretty much all there is to it. So that's your answer. So let me circle this here. And again, this video will be posted for you to see on YouTube. Okay, so that's your line integral. So I'll see you guys next time.